Okay, we're going to continue our study of objects in motion with Newton's 3 laws of motion. Newton's laws of motion describe how objects move and why they move. I have a little bit of vocabulary to start you off with here before we actually get into the laws of motion themselves. First is mass. Hopefully this is a review. You might want to copy it down again so that it's here in your notes. So if you remember, a mass is the amount of matter in an object. And we generally think about it as how heavy an object is. It can be a lot of mass, it feels really heavy to us. Not a lot of mass feels really light to us. Now I have a new vocabulary word to add in here. You've probably heard it before, but make sure you write down the definition of this word. It's inertia. Inertia is the tendency of an object to resist a change in motion. It means that objects want to keep doing what they're doing. If an object is sitting still, it wants to keep sitting still. And if it's moving, it wants to keep moving. And that's going to bring us to Newton's first law in a second, but let's get these vocabulary words out of the way first. So when we think about inertia, it's important to remember that inertia depends on mass. So an object with a lot of mass, a really heavy object, is going to have a lot more inertia than an object that has a little bit of mass, a light object. So let's look at an example here. I have two objects here. I have on the left a giant flaming semi-truck, and on the right a Mini Cooper. So which of these two has a greater inertia? Hopefully you said that the semi-truck does, and the reason for that is that it has a lot more mass. It's a lot harder to get the object moving and to stop it or to change its motion because of that mass. Okay. The next vocabulary word that I want to introduce is force. Now everyone's heard this word before, but let's look at it in terms of physics. A force is simply a push or a pull. So anytime you push or pull something, you are exerting a force on it. Now for physics, we need to remember that forces have both a size and a direction. So we have a number, an amount of force, and we also have the direction of the force. So take a second here, pause the video if you need to, jot down some examples of forces that you can think of in just day-to-day world. Now, the next vocabulary word is net force. Net force. Net force is the total amount of forces acting on an object. So it's a combination of all the forces acting on an object at one time. And in the real world, that's a lot. It can be a lot of forces like gravity and friction, and maybe you're pushing down on the chair you're sitting in right now, or maybe you're pulling on the pencil. So at any given time, a lot of forces can be acting on an object at one time. Here I have my sample object. I have a book sitting on a chair. I want to look at the forces being exerted on this book. So maybe we have gravity pulling down on it. We have the chair pushing back up on it. Maybe some friction between the book and the chair. Maybe it's windy and there's some air resistance, or maybe the air pressure around it. So lots of different forces that are acting on it. Here I just used this as an example, and I included these four numbers. I also want to show you that the value of the force, we give it a number. So here I just assigned a random number, 10 newtons. The force is measured in newtons of force. So remember, there's a value, a size, and a direction for every force. Let's look at some of these in more detail. Okay, so when we calculate net force, again, net force is the total amount of force acting on an object. We're going to look at all the forces. And here again, to simplify it, I used 4 different forces. Important to remember that when the forces are acting in opposite directions against each other, you subtract the numbers. If they're working with each other in the same direction, you add the numbers. Make sure you write this down. When they're working opposite of each other, you subtract the numbers. When they're working with each other, you add the numbers. So here, if you look at these arrows, they're all working opposite of each other. So if we were going to find the net force, the total amount of force acting on this book, we would subtract these numbers. So 10 minus 10, 10 minus 10 is 0. So there's actually 0 amount of net force acting on this book. It seems kind of strange because of course there's forces acting on this book, but when you take them all into account, they're balanced out. 0 net force, and that's going to be important in just a second. Let's look at a couple other examples. So here I just simplified it and made this a green box, and here are some forces working on the object. Again, you're going to look at the size of the force in numbers and the direction of the force, which I indicate by the arrows. Remember that opposite forces are subtracted. So if we look at these two 5s, they're working in opposite directions, so you subtract them. 5 minus 5 is 0. Here we have forces acting in opposite directions, but notice the numbers are different. So 20 minus 15 is 5 newtons. So now we have a total of 5 newtons of net force acting in this direction. Okay, so that means that something is pushing harder from this side than this side. Here again, with my orange object, we look at these are objects, forces acting in opposite directions, so you subtract. And the numbers are the same, so 12 minus 12 and 12 minus 12 are 0. 0 net force. Okay. Now, what does this have to do with anything? Well, net force actually determines what the object's going to do. So there's two options here. Either the net force is 0 and the forces are balanced, and in that case the object's going to keep doing what it's doing. It's not going to change its motion. The other option is that the net force is more than 0, and then in that case the object is going to change what it's doing. It's actually going to accelerate. It's going to change its velocity, and the balancers or the forces are considered unbalanced. So let's take a look at these two examples, one in which the forces are balanced, one where they're unbalanced. So here we have two dogs playing tug of war with a little stuffed animal, and in this case the forces are pulling away from the object, but it doesn't matter because the arrows are still pointing in opposite directions, so you subtract the numbers. So here we have 15 minus 15 gives you a net force of 0. That means the stuffed animal here is going to keep doing what it's doing. It's basically going to stay. They're at like a standstill in their tug of war. However, this one, notice these guys are moving the couch, and their arrows are pointing in the same direction. That means that you add the numbers. So the force on the couch is 14 newtons to the left. 14 newtons to the left. That means the couch is accelerating or changing its velocity to the left. So that brings us to what is Newton's first law of motion. Well, Newton's first law, you've probably heard this before, is that an object will remain at a constant velocity unless acted upon by an outside unbalanced force. Sometimes you hear it said an object in motion will stay in motion, or an object at rest will stay at rest unless acted upon by an outside force. It's the same thing. Sometimes the Newton's first law is called the law of inertia. Any guesses why? Maybe pause the video and think about it. Well, hopefully you said that if inertia is an object's tendency to resist a change in motion, and Newton's first law says an object's going to stay doing what it's doing, they basically mean the same thing. Remember, it's important that mass is a measure of inertia, and inertia is a measurement of mass. So objects with a greater mass are going to have a greater resistance. So according to Newton's first law, if you start an object moving, it should continue moving forever. But we know this isn't the truth. If you shoot a hockey puck across the ice, right, eventually it's going to come to a stop. Or rolling the ball on the floor the other day, it's eventually going to come to a stop. Why doesn't this happen? Well, that's because of friction. Friction, make sure you write this down, is the force that acts between objects that are touching. They have to be touching. So for two objects that are touching, always have friction acting between them. Sometimes more than others, but they're always going to have friction acting between them. And friction always works in an opposite direction to motion. So if you're rolling the ball this way, friction is working this way. Always works in an opposite direction. Now, friction occurs because the surface of an object is not perfect. So you always have some amount of resistance. Even things that feel smooth, like your surface of your desk or something, have little imperfections on it. So when you rub against it, the imperfections in both surfaces catch and cause the object to slow down. Now, the less imperfections, the less friction you have. So things like ice has less friction than a gravelly road. So what affects friction? Well, let's see. One is the roughness of the surface, and two is how much force you're putting on it. So if you really press hard against something, or that something is really massive, it's going to have more friction acting between it and the surface than something that's not pressing as hard. And a lot of times you can see this if you rub your hands lightly together, you get less friction than if you rub them really hard together. There are a couple different types of friction. We're going to go over that. So this one, with the boy sliding down the slide, is an example of sliding friction. Really creative name there. Sliding friction is the force of friction that acts between two objects that are sliding past each other. Ice skates on ice, someone on a slide. Sliding past each other is sliding friction. The next type, as you might, one more, is fluid friction. Fluid friction acts on objects that are moving through a fluid. One thing that's very important to remember here is that air in this situation is considered a fluid. So air resistance is actually a type of fluid friction. Very important to remember. Make sure you write that down. So any objects moving through air, things like airplanes, or anything moving through a fluid, such as swimming in water, is experiencing fluid friction. This one, if anybody knows what this is, it's a bearing for like a wheel. And this is an example of rolling friction. So rolling friction occurs when an object rolls over it. So most obvious things are like balls, wheels. Here the little bearings are sliding in between the two surfaces to decrease the amount of friction that is acting on the wheel. And then finally, we have static friction. Static friction occurs when two objects are sitting still. So if you have anything that is sitting still on another surface, it is experiencing static friction. The static friction is what is holding it in place. So when you go to push something out of place, you are overcoming static friction to make it slide. Now, the more massive an object is, the more static friction you have to overcome. Sometimes if you're pushing like maybe a piece of furniture or something, and you push and you push and you push and it finally pops free, you've exerted a force that is greater than that static friction. Now you're experiencing sliding friction, which is less. So the last thing I want you to do for these notes is to answer these 4 questions. You're going to go ahead and write these in your notes right after the last note. What would a situation be when we wanted to reduce friction? We want less friction. And then how could we do that? And then what would a situation be when we want more friction acting between objects? And how would we do that? So go ahead and write the answers to this in your notebook, and we're going to go over that as a class.